We'll now move into section 6.6, where we will introduce the inverse trig functions. Very similar to how we introduced the exponential and the log functions, we do have to start with some basics, look at some pre-calculus, look at some values, some equations, just how to use and solve these a little bit. Inverse trig is going to rely on some of our regular trig facts as well. So again, it's a lot of little pre-calculus work, but we're really trying to work towards the limits, the derivatives, and the antiderivatives. This, we're not even going to really see too much with limits. We'll eventually get a couple that will come up, but a lot of it, the derivatives and the antiderivatives, and the problems that use those two concepts. So, we're going to start off introducing inverse sine x. Inverse sine. And just very quickly, I want to point out the notation. That's typically where we use an exponent. If you wrote something like this, that would be understood as sine cubed x. So this truly equals this. But in the inverse notation, that's not really a trouble spot. Because if we really wanted to have sine to the negative 1 power, that's the one exception. You can't put that exponent here because that would be understood to be inverse sine. But that's not an issue because if you really wanted sine to the negative 1 power, that is 1 over sine, and that is cosecant. So we have an entire separate trig function for that. So that's the first thing I wanted to mention. The second thing as far as notation, our book always uses this, but other books write it like this. And instead of being read as inverse sine, it's literally read as arc sine. Now, I don't know the origin as far as why they call it this, but this is, again, I don't want to say it's equally common, but there are a lot of textbooks that use this notation. So I just wanted you to hear it one time. And just in case, for me, I learned it this way. So every once in a while, I try and use the notation and the way our book refers to it as inverse sine. But if I accidentally say arc sine at any point, I want you to be clear that this is what I'm referring to. But I'm already jumping into notation, but we got to go backwards here. Because if I go back look at plain old y equals sine x, we're going to immediately run into a problem. Because if we remember the graph of sine, there's a quick sketch of the sine curve. The high values are 1, the low values are negative 1. But do you notice an issue? For us to define an inverse function, the original has to be 1 to 1. And this is not. I mean, just look at the x-axis. The x-axis is a horizontal line, and it hits the graph in an infinite number of spots. I mean, right now, we see 6. 1, 2, 3, 4, 5, 6 spots. But remember, this just keeps going forever. So the x-axis would just hit the graph an infinite number of times. I mean, plenty of horizontal lines that never hit the graph anywhere. But the issue is this middle area. So what we have to do here, we have to play a little game. We still want to define the inverse sine, but the issue is because the original does not satisfy the horizontal line test, the original function is not 1 to 1, what we have to do is restrict the domain. Typically, the domain from sine goes from negative infinity to positive infinity. You could use any angle. But what we need to do is cleverly cut the graph off. We still want the same range. The range of sine goes from negative 1 to 1. But what I have to do is I have to cut the domain so I still get the full range, and what's left over will be 1 to 1. What's left over will pass the horizontal line test. So we could do this in a lot of different places, but the easiest place is to kind of stay a little centered on the origin. So we'll have to go left and right. That if I cut my graph off here on the left side and here on the right side, and now I ignore everything else. So just this little piece, I still go from the low value of -1 up to the high value of +1. So I still get the whole range, but when I ignore everything to the left of this line and everything to the right of this line, everything just in between these lines, now that is 1-to-1. So what is this restriction? What are the x values that cut the graph off here and here? Well, it takes 90 degrees to reach our first peak, and the odd symmetry here, -90, to go this way and get to this valley. But remember, we are not using degrees though. We have to stay in radians, so that'll be -π/2 to +π/2. Now, inverse sine is well defined. We now have domain restrictions. Inverse sine, if I say something like inverse sine of 2, that's undefined or does not exist. That's garbage. What was the range becomes the domain, but think about that flip relationship. And let's even write this generically for all trig functions. We talk about the inverse trig. There's 6 regular trig functions, so there's 6 inverses. But for this section, we're only going to focus on the primary 3, inverse sine, inverse cosine, inverse tangent. And actually, when we get to the real calc portion, it's really only inverse sine, inverse tangent. But in general, all the inverse trig, we still have that same relationship. Trig function is has an original input of an angle theta, and the output is some value. And that value we could think of as the ratio of sides in a right triangle. If it's sine, that value is the opposite over the hypotenuse. If it's cosine, it's adjacent over hypotenuse, etc. But what I'm really trying to get us used to right here is that inverse flip. Then now it's the inverse trig function of a value takes me to this angle. So what is the angle? This question is saying, what is theta such that sine of theta equals 2? And this first one was garbage because sine only goes between -1 and 1, so it never equals 2, and that's why this answer does not exist. So maybe instead of starting us off with a tricky one, and let's just move right into it, let's get a few more. Let's evaluate inverse sine of 1/2 and inverse sine of, we'll do radical 2/2. They're just the flips. Again, we're going to need some of these values, everybody. Just like you saw with exponentials and logs, e to the 0, log of 1, these things come up. So we're going to need some values here, and calculators help. Just be careful, radian or degree mode. If you're in degree mode, you would get a degree answer. You just have to convert that to radians, okay? If you're in radian mode, most of our calculators are not going to give us nice radian answers. But it's thinking backwards, right? How do I know this value? Go back to that chart I gave you in that introduction video. I'm talking like our review video. Remember some trig facts. And we're used to using a chart like this by saying something like sine of 90 equals 1. Sine of 45 is rad 2/2. But now we're just doing it in reverse. We know the trig function. I want inverse sine, so look at sine, but go backwards. Find the right value and go backwards to the correct angle. So inverse sine of 1/2 is π/6. And that's what I mean, everybody. A calculator can help, but if you're in degree mode, you get 30 degrees. You should be able to convert 30 degrees to π/6 without too much trouble. But if you're in radian mode, I guess there are a few of the newest calculators that would give you an answer π/6, but most of your calculators, let me show you on mine quickly, you're going to get an ugly decimal that's not going to help you at all. So inverse sine, second sine button, 1/2 0.523, blah, blah, blah. Now notice, I know the answer is pi over 6. So by putting pi over 6, I can confirm that this is the same thing as this. But again, that was because I already knew this answer. Very few of us would look at that and go, oh, that's pi over 6. Yeah, that's quite a stretch. So calculators don't help us too much here unless we do some conversions on our own. And again, these are things we should know. Just as easily, so inverse sine of rad 2 over 2, well, that takes me to pi over 4. How can this get tricky? The truth is, it really can't. Because even if you get negative values, what's inverse sine of negative 1/2 and inverse sine of negative rad 2 over 2? We'll go back to the original graph. I know I'm looking at the graph of sine, but I'm just flipping my inputs and outputs. And look, over here, a value of 1/2 went with an angle of pi over 6. Look on the opposite side. All the symmetry here, negative 1/2 would go with this x, and this x is just as far away from the origin, but in the other direction. This answer would be negative pi over 6. And I know that's only one problem, but a lot of us see a really, really nice shortcut that if it's a positive value, you just get the positive reference angle, and if it's a negative value, you just get negative that same answer. So negative 1/2 went with negative pi over 6. Negative rad 2 over 2 would go with negative pi over 4. So that's a good start. Let's keep going here. I mean, again, in a pre-calculus class or possibly in high school, depending on when you initially learn this, you should have seen this somewhere along the way. You should have had a section where they kind of work you a little harder to check these little restrictions, and I'll show you some common. Actually, let's even do one right here. If we compose sine and inverse sine, they cancel, but only if you're in the proper restrictions. So inverse sine of sine, let me just do this in degrees. I know, again, calculus, we need radians, but just to make this a little bit easier for a lot of us, if I said inverse sine of 120, these don't cancel. And that's because 120 degrees is not in the domain for inverse sine. So if this was inverse sine of 20, 20 degrees is between negative 90 and positive 90. They'd cancel and you'd get 20. Let me even write that out. Because essentially, again, these are just canceling. They're undoing each other. But right here, that's not in the right restriction. So I'd have to think about reference angles. Well, 120 is in the second quadrant. Sine is positive in the second quadrant. But 120 is out here. So I need an equivalent that's inside of here. And that equivalent would be 30 degrees. Sine of 30 is equal to sine of 120, but now 30 degrees is in the proper window. So I wanted to at least point that out. I'm not looking to bust your chops with this. As we get a little further along, every once in a while you'll notice the book makes these extra little qualifiers, and those qualifiers are based on those initial restrictions. But that's not what we need to focus our attention on. We need to quickly get past this pre-calculus so we can get into the derivatives and antiderivatives. So I'm going to move right along. I'm going to skip cosine for a quick moment. I'm next going to look at tangent. And you'll see why I picked to go to tangent next. Again, just a second. I'm going to think about the graph of tangent. Tangent, like all the trig functions, repeats itself. So just like sine, the issue is this is not one-to-one. This does not pass the horizontal line test. So we once again have to restrict the domain, but we want to keep the full range. The range for tangent goes from negative infinity to positive infinity. So we need to find a nice restriction that'll still keep that same range. And the reason I followed up sine with tangent is because these asymptotes already do that nicely for us. I could go from here to here. Ignore the cycles before and after this primary cycle, and that will give me the full range, and that restriction, well, this asymptote, remember, tangent is sine over cosine, so when is cosine not defined? Here and here, at negative pi over 2, at negative 90, and at positive pi over 2. Cosine is 0 there, so sine divided by cosine will give us something divided by 0, a k over 0, and that's why we're getting these asymptotes and why the graph shoots off to the infinities. So the domain here, the only catch, this is so similar to what we just did up here for sine, the only catch is that these are parentheses. Parentheses negative pi over 2 to positive pi over 2. That's the only catch. So still the same trick. If I evaluate inverse tangent of 1, when does tangent equal 1? Well, this is why some people like a third line on this chart. Tangent comes up often enough that they just want to be able to see and look, but we could think, when do we divide sine divided by cosine and get 1? And it happens right here. When you divide the same thing by itself, that's when you get 1, and that happens at pi over 4. But now, what if it's inverse tan of negative 1? This has the exact same property. The negative 1 over here would kind of be, talking about symmetry, a reflection across the origin from the value of 1 that we had here. So if 1 went with pi over 4 here, well then negative 1 goes with negative pi over 4 here. Exactly the same that we saw for sine. And I could keep playing the games with the restrictions, same thing. Inverse tan of 120 would be the exact same 30. For the same reasons. 120 is not in this window, so you need to find tangent at a different angle that has that same value. I'm actually sorry about that. I would actually have to go in the first quadrant. Yes, tangent in the second quadrant would be negative. So inverse tan of 120 would be negative 30 because tangent would be negative in the second quadrant. But still, similar restrictions. I'm focusing on this restriction this way. If you go the other way, it's just about making sure you're in the proper range. So if I had sine of inverse sine of negative 3.2, that's garbage. This doesn't make any sense, just like this didn't make any sense, so you can't keep going. This right here is undefined, so sine of that is undefined. So again, it feels so tempting to just cross these off, but with those extra restrictions, we just have to be careful that everything is in the right interval. So this would be a does not exist. So again, back to here, tangent of 1, that all works fine. What if I had the limit as x approaches infinity of inverse tan x? I can't ask you what is inverse tan of infinity, but this is where a limit comes up. So we still have to do that same inverse thinking. What is the angle where the y value in tangent goes to infinity? And that's right here. So this would equal pi over 2. So I can't say inverse tan of infinity equals pi over 2. That's nonsense, right? We can't plug infinity in as a number, but as a limit value, that does make sense. Okay, so that's really the only limit we're going to bring up here. Mostly, again, we're focusing on the domain and range, the restrictions that we have to make, and so far, not so bad. Negative 90 to positive 90 for sine and cosine. If the value is positive, then the angle is positive. If the value is negative, then the angle is negative. And these are the two we're going to focus on with respect to the calculus. But I do have to mention cosine very quickly here. Cosine has to get mentioned so then we could see why cosine is not necessary. So let me finish this with cosine. Cosine, well now this would be my cycle of cosine, starting at 1, down to -1, up to 1. Still doesn't pass the horizontal line test, so still not 1-to-1 like all the other trig functions. Initially, the domain is -infinity to +infinity, but we're going to have to restrict it while keeping our range from -1 to +1, just like we had for sine. Now, after seeing those previous two, a lot of people want to say, why not keep the same restriction? Go from -90 to +90, but realize here, -90 to +90, you still wouldn't pass the horizontal line test. And then as a double whammy, you don't even get the full range. If you only go from here to here, you're only getting the positive y's, you're not getting any of the negatives. So for cosine, we need a separate restriction, and cosine goes from here to here. 1 to -1 on the y scale, and that'll go from 0 to pi on the x-axis. So these evaluate problems, they still start nice and easy. What's inverse cosine of 1/2? Use your chart, positive, nothing fancy. Positive 1/2 takes me to pi/3 on the cosine line. So that first answer is pi/3. Since cosine of 60 equals 1/2, well, inverse cosine of 1/2 equals 60. Still getting that nice inverse relationship. But here's the pain in the butt. Inverse cosine of -1/2. From everything else we've done, just want to say -pi/3. But that doesn't work. Pi/3 takes me to 1/2 here. -pi/3 still takes me to 1/2 here, not -1/2. I have to come down in here. This is pi/2. I know I'm looking at this graph, but I have to think of my unit circle and think about getting in the second quadrant. There's pi/2, there's pi. So what's the angle inside of here? The whole angle that gets me to that -1/2. And it's just about reference angles, everybody. If 60 degrees or pi/3 gets me to 1/2, well, I still have that same reference angle, but I just have to convert that to a regular angle. So if this is 60 degrees right here, then this is 180 minus that 60, 120, which is 2 pi/3 radians. Again, I realize that's not easy, and this is where, like I said, you should have had a class earlier where they kind of pushed you a little bit harder with these restrictions just to make these functions make sense. I'm not even looking at the graphs of the inverse functions because I don't need them. All I need is this inverse relationship, and we could use the chart that I've been showing you to get the values. But now, last little bit of pre-calc, and then we'll move right into the derivatives. We're not always lucky enough to compose the same trig function with its inverse. And, we shouldn't expect things to cancel, but the nature of trig functions is that some interesting things happen. So, if I wanted you to simplify cosine of inverse tan of, let's start nice. Let's start off with 3/4. I'm saying nice, I'm giving you a numerical value. We'll do this in a moment with variables, and that is what we are going to need moving forward. But let's still start nice here. So cosine of inverse tan of 3/4. Realize this is some angle. And I actually don't need to know what that angle is. When you have numbers, a calculator can just solve this for you without any difficulty, but it doesn't It doesn't replace the understanding that we need. And again, without numbers here, our calculators can't help us. So this equals some angle theta. So tangent of theta is 3/4. Inverse tan of 3/4 equal theta. Tangent of theta is 3/4. These are both the same thing. But by recognizing that this is some angle, this problem really wants us to figure out what is cosine at that angle. And I don't need to know what the angle is to know that. All I need to do is make a right triangle and use our right triangle facts. For cosine, I like to just stick my angle theta in this corner, and with this basic setup, my opposite side would be 3, my adjacent side would be 4. I'd use Pythagorean theorem and eventually figure out that the hypotenuse is 5. 3 squared plus 4 squared equals blank squared, and this is a nice relationship. And now I can come back and say, well, what's cosine? Cosine is adjacent over hypotenuse, so 4/5. But now, that's a nicer example. You need to understand this work, but this is where if you did this on a calculator, you get 0.8 and it's all the same thing. But let's look at a second one. What if I wanted secant of inverse sine of x over 4? It's the same thing, everybody. This is some angle theta. So I'm going to set up my right triangle. I'll draw it a little bigger this time so I have a little more room to work. And now I know sine of theta is x over 4. So for tangent, we use the 3 was opposite and the 4 was adjacent. Tangent is opposite over adjacent. For sine, it's opposite over hypotenuse. So the x will go over here for the opposite, the 4 for the hypotenuse. I need this side. Careful with Pythagorean theorem, everybody. It's a very natural temptation. People go this squared plus this squared equals this squared, and that's correct. But realize you can't go x squared plus 4 squared equals this squared. The hypotenuse has to be the side by itself. So x squared plus blank squared equals 4 squared. Solve for my question mark. 16 minus x squared. Take the square root. Technically we get a plus or minus. But again, this is where those extra angle restrictions, we get to ignore the negative. Just think of this as distance. Now my right triangle is set up. Well, I really want secant at theta. Well, before I get secant, let me get cosine. Cosine would be adjacent over hypotenuse. So secant would be the flip. And again, calculator does help you here, but calculator does nothing for you here. We did something like this in that little trig review at the very, very beginning, and now is a good reminder. And next chapter, chapter 7, we're going to have to do things like this on our own. Okay, so now, a lot of background work, but now we really start moving into the calculus portion. And let's get started with derivatives. I'll quickly show you the derivatives for inverse, sine, tangent, and cosine, and we're going to make a little chart and we'll practice using them. But first things first, before I just give you the answers, let's find the derivative for inverse sine x. And it may be surprising, but I'm going to use a little trick. I'm not going to use the definition of the derivative. I'm going to use a little trick just like I did for log. I'm going to think of this as y equals inverse sine x. I want dy dx, but I don't know it. So I use the inverse. Either I take the sine of both sides, and I assume I'm in a good region, so this cancels. Sine of inverse sine of x is x. Or I just directly apply the inverse. If y is inverse sine of x, then sine of y equals x. I want the derivative, but now I need to take that derivative implicitly. So over here, the variable is y, but the derivative of sine y is cosine y, but then it gets marked dy dx equals the derivative of x is 1. It is an x with respect to x, doesn't need any extra marking. So it seems like dy over dx is 1 over cosine. But just like we did with log, I want the derivative of this function with variable x, so I want the derivative in terms of variable x as well. So 2 ways to finish this. Option number 1 is to do what I just did up here. Come back to this line and realize that if I know sine of y is x, I could treat that as x over 1. I can make a right triangle with angle y for cosine x over 1. Use your Pythagorean theorem. You'll get radical 1 minus x squared here. And now what is cosine of angle y? Adjacent over hypotenuse. And this divided by 1 is just this radical. Notice cosine is in the denominator here. So that's how I get that radical in the denominator. I'm literally getting 1 over this, and the radical over 1 is just the radical. There are other ways I can make that last little conversion, but that's ultimately the point. Inverse sine of x has this as a derivative, so already preparing for chain rule. Inverse sine of u has derivative 1 over radical 1 minus u squared times du. Okay, I'm gonna want to make this chart. I want to show you the others as well. So the next, let's jump right into inverse cosine. I know I did inverse tan next, but I want to show you right now why inverse cosine will be unnecessary past this point. We need to understand the basics of it just as a function, but why we're not going to need its derivative. The book lists it. The book does give you the derivatives for the other 3 inverse trig functions as well, but you'll see, kind of like I said in a previous unit, we're adding more to our f prime chart that we're responsible for, but I'm also trying not to make it a huge new list. So instead of having 6 new functions, we're only going to need 2 as we go past this chapter. So let's just focus on those 2. So quickly, let me show you inverse cosine of x. And I'm going to do it the same way, everybody. Y equals inverse cosine. So cosine of y equals x. Take the derivative with respect to x. I get negative sine y dy dx equals 1. So dy over dx is 1 over negative sine y. Go back to here. Cosine of y equals x over 1. Cosine adjacent over hypotenuse. So when you finish this third side, you get the radical 1 minus x squared over here. You want sine. Opposite over a hypotenuse. So this over this, it's the same thing. You're just getting an extra negative. So the derivative of negative inverse sine is the same as the derivative of inverse cosine. So as a derivative, that's good to know, but we're really doing this for antiderivative purposes. So I don't need this up on my chart again. I'm not going to need 2 different antiderivatives for the same piece. That if the negative is there, it's inverse cosine. If the negative not, it's inverse sine. That's unnecessary. If the negative is there, just put the negative in front of the inverse sine. So nice to realize, but again, unnecessary. So let me finish with inverse tangent. So H is inverse tangent. Y is inverse tangent. So tangent of y is equal to x. Taking the derivative. The derivative of tangent is secant squared, but there was a y, so it gets marked. And one more time, the derivative of x is 1. I divide the secant squared over, and I still need my conversion. This time, my right triangle. I've got x over 1, but this time it's tangent, so x is my opposite, 1 is my adjacent. Pythagorean theorem. We get this. Well, actually, I'm sorry, one more step. Instead of leaving this as 1 over secant squared, realize that's the same thing as cosine squared, right? 1 over cosine squared is cosine squared. So cosine of y adjacent over hypotenuse, and then we square it, 1 over the square root squared, and the square root would cancel. And again, just converting that, inverse tan of x has derivative 1 over x squared plus 1, so 1 over inverse tan of u would have derivative 1 over u squared plus 1 du. Those are the two new ones we're going to add to our chart. And now I'm going to immediately move into using those. So a lot of background, and you'll see in just a few minutes, even a few derivative problems. If we do some tangent line type stuff, we're going to need a little bit of that information. But now, focusing on the derivatives. Let's find the derivative. And let's start number 1. Let's start a little simple. Let's find the derivative. Let's look at a of x is equal to 5 inverse sine 3x minus 1 plus inverse tan of x cubed minus 5x. We have to get used to chain rule. I'm not even doing a basic one. We just proved if it's inverse sine x or inverse tan x, but anything more than that, whether it's just a little extra 3x or a 3x minus 1, or it's an extra x cubed instead of an x or an x cubed minus 5x, that doesn't matter. These are both u. So this is not multiplication. This is not product rule. Same thing over here. There's no product rule over here. Two separate pieces, both have inner, outer, so both need chain rule, and they're separated by addition. So I can take my derivative, the 5 pushes along, the derivative of inverse sine, similar to log. You don't take the derivative and then end up with an inverse sine over here. You take the derivative, the inverse sine or the inverse tan is gone, and you start getting this ugly fraction. And whatever was u in the original function is the new u over here. And that u is squared, and then at the end we get the times du. That's how we make that rule work. So the 5 pushed along. Inverse sine, 5 times that, so 5 times. 1 over radical 1 minus u squared. U squared. The derivative of inverse sine, 1 over radical 1 minus u squared. U here is the same u here, but at the very end I get a times du, so now I go to the inside, and this just gives me an extra times 3. Almost the same thing here. Plus, don't have a number out in front, certainly could write a 1 if you want, but now I'm jumping right in. Inverse tan 1 over u squared plus 1. Inverse tan, there's the basic part of the derivative, 1 u squared plus 1. But then du, inside now I take the derivative of u, and I get times 3x squared minus 5. This is a perfectly good answer. I mean, the little things that we've always discussed, the book loves cleaning everything up. We've got a 1 over times du. Those can go nicely in the numerator. Here, both of these can become a nice 15. There's no good reason to square these out, though, everybody. I mean, if this was just a simple 3x, actually, let's even do that. So that was the correct answer the way it was. But now let's get rid of this. So now this would just be 3x quantity squared. Sure, that's worth your time to make that a 9x squared. But anything more than that, just leave it. There's no good reason to FOIL that out. This is 3x squared minus 5. We'll leave that alone. And still have the plus 1 at the end. For us, that's as good as these derivatives are going to get. Okay, couple of quick little things. I like to write the u squared here, u squared plus 1. Some people do 1 plus u squared. It's the exact same thing. But for inverse sine, the u has to be at the end. U squared minus 1 and 1 minus u squared are completely different, everybody. So just be careful here. With inverse sine, that has to be at the end. Radical 1 minus that term squared. So let's get more practice, though. Let's move into number 2. We'll look at b of x. And for b of x, let's mix some old stuff together. Let's look at e to the x squared inverse tan of 3x to the 5th power. Okay, we're still taking a derivative, but we still want to observe the situation. Looks pretty messy here, but what's the connection? All of this is being multiplied by all of this. Once again, there's no multiplication here. But this times this is multiplication. There is no multiplying it out. This is product rule. But now both this and this are both, we could look at this as e to the u and inverse tan of u. So they both are using chain rule, but hopefully we're getting good practice that, again, chain rule should not throw us off. The big thing here is that this is product rule. So for me, I do my product rule, derivative of the first, plane second. Actually, I'll write it out. So u prime v plus v prime u, assuming this, sorry for that scratch, this is your u and this is your v. So I'll just go through and do it. No harm at all. A little bit harder of a rule, product or quotient rule, to write a little work off on the side and then plug it in. That's fine. But again, just with a little practice, we can do this. The derivative of e to the x squared is itself times an extra 2x. E to the u du, I'm just moving that du to the front, times the original second, times inverse tan of 3x squared, plus, now I do the derivative of inverse tan, similar to what we were doing up here, 1 over u squared plus 1 times du. Right? There was my u. Now, some of you might be like, well, you're using a u here. Now it's a different u. Use different letters if you need to. We need to. I mean, we're in Calc 2. We need to have that flexibility to substitute different letters if need be. So you could certainly do that. Or again, just use the word inside. Inverse tan of inside is 1 inside squared plus 1. 1 over, I'm sorry. Inside squared plus 1. Derivative of the inside. That works. All that is the v prime times plain old u. A good answer. This is definitely as good as it's going to get. Okay. Over here, little things, like I was kind of saying up here, this is simple enough. Just if you square it, don't forget to square the number as well. So you get 9x to the 10th plus 1. And in the top, just realize this is over 1, this is over 1. So all this can go right in the top, 15x to the 4th, e to the x squared. Okay, number 3, we'll do one more basic derivative, and then I'll do a critical value and a tangent line problem. So one more basic derivative. Let's look at inverse sine of cosine x. All I'm going to do is just jump right in and take the derivative. Again, nothing crazy. There's no multiplication here. Inverse sine x cosine x, that would be product rule. But inverse sine, parentheses, this is inner. So this is inverse sine u. So it's a pretty straightforward 1 over radical 1 minus u squared times the derivative of u. And now, a lot of us, from what we're seeing, we go, oh, okay, no big deal. And we get this answer, and then we check the back of the book, and we get frustrated because we see the answer is -1. Do you see where this came from? It's a coincidence, everybody. I mean, we've had plenty of stuff inside our inverse trig functions, but when you start mixing regular trig inside inverse trig, sometimes funny things happen. Specifically here, an identity pops up. Do you recognize this? 1 minus cosine squared is the same thing as sine squared. What I'm really using here is sine squared plus cosine squared equals 1, but how you can manipulate that. So if you subtract cosine squared on both sides, you'd get this, and that equals sine squared. And the square root of sine squared, I could cancel the square and the square root and get sine and negative sine over sine. That's why it equals -1. So like I said, I'm not trying to make you go crazy with cleanup. I think I've pointed out a little bit. Definitely leave that alone. But simple things, it's a good idea to square. But definitely to realize, sometimes with the trig functions, just identities just kind of pop their heads in. So it wasn't really that this was inverse. It was that the inner part also had a trig function, and then a little coincidence that an identity popped up. So just at least be aware that something like that could happen. But now, we'll finish up this part of the video, and then we'll move into the antiderivatives in a separate part. There's a lot to be said there, so we'll get to that in a separate part, but let's practice using those derivatives. Let's take a look at this problem. Let's start with find the critical values for the function. And again, nothing too crazy. Let's look at 2 inverse sine x squared. I hope you're starting to realize I expect you to be able to handle some basic derivative and antiderivative problems. For the derivatives, I'm not going to go too crazy, but you should be able to find the critical values and the equation of the tangent line. We're not doing any of the concavity, increasing, decreasing, local max min stuff. So I'm trying to keep your list of everything you have to remember from Calc 1, keep that list a little light. And then for the integrals, the area under the curve. So critical values, where the derivative is 0 or undefined. Well, first thing I need is the derivative. 2, 1 over radical 1 minus x squared squared, so that's x to the 4th, times du, that's 2x. This is good, but again, good habits. If you're going to set this equal to 0 and look for where it's undefined, we should clean it up a little bit. So when does this derivative equal 0? It's one fraction, so we just set the top equal to 0, and we get a nice quick answer. X is 0. But when does the derivative not exist? When is the derivative undefined? When the denominator equals 0. So again, combining that into one fraction made this a lot easier to just top equal to 0, quick answer, bottom equal to 0. Well, this is a little bit tougher. Some of us, we square both sides, but 0 squared is still 0. And now we're factoring. 1 minus x squared, 1 plus x squared. This one can still keep going. 1 minus x, 1 plus x. This one, when you set equal to 0, you get no solution. X squared equals -1. We're not getting any imaginaries, but each of these will get x is plus or minus 1. So all of these are the critical values for this function. So, quick one. This one wasn't too terrible. Derivative wasn't too bad. Just a good reminder on the overall process. Quickly to point out, if the original function was 2 inverse tan x squared, you get a similar derivative. You'd end up getting 4x over x to the 4th plus 1. I just wanted to point this one out because now that we're starting to see more fractions with our derivatives, we have to be more aware about setting the denominator equal to 0 and trying to find those extra critical values. But you realize you don't always get an answer. Here, you'd set, so this, let me call this one e of x. So this would be e prime. And you'd still set the top equal to 0 and get 0. But if you set the denominator equal to 0, you get no solution. So this one would only have a critical value of 0. You still wanted to not forget about the denominator, but just to realize that's just a coincidence. This problem did not get any extra critical values from that situation. Okay. And now we'll find the equation of the line tangent to the function. What are we up to? That was e, so this will be f of x. We'll look at 4 inverse tan 3x minus 4 plus 2 e to the x squared minus 1 minus 12 log 2x minus 1. Find the equation of the tangent line to this curve at x equals 1. Any of these problems, everybody, we're starting to see multiple examples. Both these problems, you have to take the derivative. Doesn't matter that in this one that I've got, inverse tan 3x minus 4. Doesn't matter this one combines inverse tan e and log. No, it does not. How do I get the tangent line? I need an xy pair, and I need the slope. Well, I have the x. I'll plug that in to get the y. Plug that in. 4 inverse tan 3 times 1 minus 4 will give me minus 1. Plus 2 e 1 squared minus 1 will give me 0. Minus 12 log 2 times 1 minus 1 will give me 1. 4 inverse tan of negative 1. When does tangent, at what angle does tangent equal negative 1? At negative 45. But again, calculus, negative pi over 4. 2e to the 0 is plus 2. 2 times 1, so plus 2. Minus 12 log of 1. Natural log of 1. E to what power gets you to 1? This goes to 0. So this becomes, the 4's cancel, minus pi plus 2, or some people would rather write it 2 minus pi, but that is your xy pair. Feels a little weird to see something like that, but that's legit. And we don't want our calculator, we don't want 2 minus 3.14 is negative 1.14. That's rounded off, leave the pi. The second part here, the derivative for the slope, so f prime of x, so 4, 1 over u squared plus 1 times du plus 2 pushes along, e to the u times du minus 12 pushes along times 1 over u times du. So again, good practice with the other derivatives as well. You could plug the 1 in here. I choose to clean it up a little bit first. But notice with my cleanup, nothing too crazy. 12 on top, leaving this alone. 3x minus 4 squared plus 1. Still not foiling that out. Right here, just bringing that to the front and multiplying these out. plus 4x e to the x squared minus 1. And here, putting these in the numerator, minus 24 over 2x minus 1. Cleaned up derivative just makes my life a little bit easier as I plug my x coordinate in. And I'm going to do work as I go along. 12, plug this in, minus 1 squared plus 1 will give me 12 over 2. Plus 4 times 1 times e to the 0 minus 24 over 2 times 1 minus 1. Again, you could do a little more in your head. You could do a little less. You could write a little more out. You do what you need to. But now I'm ready to clean this up. This happens to all work out very nicely. 6 plus 4 minus 12 will give me a slope of negative 2. There's my xy pair. There's my slope, y minus, and this is what I mean, right? This is a little ugly, but that's perfectly legitimate, equals m times the quantity x minus 1. And I'm not even going to try and put that into y equals mx plus b. It's not impossible or anything. You're still going to get an extra pi. Actually, why not? I'll do it. I would get minus 2x. I would get a plus 2 here. Minus 2. Add to the other side would make that a plus 4. And this would be a plus pi. That would have to subtract as a minus pi. So again, you can do it. Just certainly a lot nicer to just leave it just like that and to be done. Okay, so the next part, we'll still be using this chart, but now we'll see how we do this with antiderivatives, and a lot of it is going to be more u substitutions.